to the same hybridization which I discussed in the previous AV. Just let me tell you hybridization, what is that? Once again, let me define it and let me tell you points, and after that we'll be drawing some diagrams. Also, I will tell you that how to find the type of hybridization, because see, you have read in VSCPR theory. What you studied there? We studied how to find the shape of the molecule. See, here also we will be finding it out, but from the hybridization, the shape of the molecule. Alright, we will be knowing about the bond length, about the bond angle, about the nature, a lot of things we are going to study. So hence, it's very important. Alright, listen to these particular AVs and understand it properly. So hybridization, I told you, it is defined as the, first of all, hybridization is a concept. Alright, you need to understand. It's not a process, it is not a, what you can say, law. It's not a principle, it's not a theory. Alright, it's a concept. We can say that you need to understand. Concept means suppose I am teaching you now. Suppose some other teacher comes and teaches you. So definitely the concept is going to differ from one person to another person. That is called as a concept. We can say that. Clear? So hybridization is nothing but it's a concept. It's defined as the mixing of the atomic orbitals. Alright? Belonging to the same atom. Alright? Listen to my every word. Belonging to the same atom, but having slightly different energies. Means they have got comparable energies. Got it? So that a redistribution of energy takes place. I have told in my last AV that whenever the atomic orbitals combine, they do not combine with one another directly. What happens? First, the redistribution of energy takes place. So that the redistribution of energy takes place between them, resulting, alright, after the redistribution of energy, then the orbitals, they undergo what you can say, the bond formation, they undergo the combination. Got it? They undergo the overlapping, we can say that. So, resulting in the formation of new orbitals, which is called as hybrid orbitals, having equal energies and identical shape and symmetrical orientation in space. Means the shape is also what you can say identical. Identical shape and symmetrical orientation in space, both are same word, so to say, we can say that. The meaning is the same. So, I said you already, so before combination of atomic orbitals, the redistribution of energy takes place so that each orbital has got equal amount of energy, and the orbital which is being formed is called as a hybrid orbital. Alright, it is being formed, that's called as a hybrid orbital. This is called as hybridization. So just to explain you an hybridization, let me tell you that you know pink is a color which lies got it? Pink is a color which lies intermittent in between white and red. So you do one thing, you just take that is nothing but a white paint, a box, or a what you can say, that is a container having white paint. Similar container you take it of a red paint and you mix with one another. What you will be getting it when you have mixed uniformly, you will be getting two container of pink paint. Alright, two container you will be getting it. So pink is nothing but the hybridized, that is color between red and that is what you can say white. Alright. Similarly, it is being what you can say considered that mule is what you can say it's a hybrid of horse and a donkey, isn't it? Similarly, pink paint is a hybrid between red and the what you can say white paint. How many? How much container we have taken white paint? One container. How much container red paint? One container. How many container pink paint we got? Two container. Because same number of atomic orbitals will give same number of hybrid orbitals. Alright. So I think you got it some idea about that is the hybridization. We can say that. Now when a particular what you can say lobe is there in which particular orbitals or in which particular subshell? P subshell, we can say that. P subshell has got two lobes which are of equal size. Now listen carefully. So this is of equal size. Now this is known as unhybridized lobe. If the two lobes remains equal size after hybridization has taken place, if the two lobes are equal size, listen very carefully, then these two lobes are called as unhybridized. They do not undergo hybridization. So which what you can say, in which condition they do not undergo hybridization? In which condition the two lobes will be of same shape or size? When that is pi bond. Because hybridization does not take place in pi bond. Pi bond never undergoes hybridization. Always hybridization means head-on overlapping, sigma bond. Sigma bond always what you can shows hybridization. sigma bond. Pi bond never undergoes hybridization. So hence, for that particular purpose, that is after the hybridization has taken place, the lobe which remain unhybridized, that is nothing but the pi bond. Because again I said, the pi bond never undergoes hybridization, because in hybridization exchange of energy takes place, and in case of pi bond the overlapping which is taking place, it is a very minimal amount. So the exchange of energy, the redistribution of energy is a very small amount of redistribution of energy is taking place. And moreover, pi bond is a weaker bond. It's a weaker bond, it's not a stronger bond. So hence that will not result in the formation of a stable molecule. We can say that. Clear? For that reason, pi bond never undergoes hybridization. Always sigma bond, that is head-on overlapping, where the exchange of energy, where the redistribution of energy takes place completely. We can say that. So hence sigma bond undergoes hybridization. So when sigma bond undergoes hybridization, these two lobes will be, one lobe will be bigger and the other lobe will be smaller. Generally, the bigger lobe is a positive charge, and positive sign is given, and negative sign is given for the smaller lobe. Now, it is not a charge. This is positive charge and negative charge. No, nothing to do with the charge. Just we are giving a symbol that is positive and then negative sign. The bigger lobe is positive, and the smaller lobe is negative sign is being given. Got it? When it undergoes hybridization, this is known as a hybridized lobe, and this is an unhybridized lobe. It does not undergo hybridization. Remember it. Got it? So during hybridization, one lobe is bigger, another lobe is smaller. Why it is? Because I've said you earlier also, lobes are made up of what? Energy. So energy is what you can say, the electron density is more in this particular case when the hybridization takes place. Got it? You'll see in the diagram I'll draw it, that when the hybridization is take place, the electron density is more this side. So more means definitely this lobe becomes bigger and this lobe becomes smaller, because electron density is less here. So it becomes smaller because lobes are made up of energies, energy levels, we can say that, sub-levels we can say. So hence this is bigger and this is smaller. This part undergoes bond formation, this part does not undergo. So one it does not undergo, it becomes smaller, and the one which undergoes bond formation, where the electron density will be more. Got it? Energy released will be more. Energy released, remember that, because when the bond formation is taking place, when the atoms they come closer, got it? What happens? The energy is released. For that particular purpose, remember it, one thing. Got it? So this is a condition for hybridization I am saying you, or it's important condition for hybridization, that hybridization does not take place in isolated atoms. Isolated atom. For example, an oxygen atom is there. Got it? Hybridization is not going to take place there. Why? Because when the two atoms they approach each other, then what happens? Energy is released. You know that. When the two atoms or the two electrons, two atoms mean to say the two electrons which is present in the outermost shell, they approach each other, then only the energy is released. And this release of energy only allows the electrons to, what you can say, migrate or to jump from the lower subshell to the, what you can say, higher subshell. To jump from the innermost subshell to the outermost subshell, from the P subshell to the D subshell, the empty D subshell. Got it? For that particular purpose, where from the energy will come? When the two atoms, remember it, not an isolated. Isolated means single atom. Got it? For example, oxygen atom, nitrogen atom, helium atom, this. In this particular cases, hybridization does not take place. Remember it. Got it? Why? That's the reason I am saying you. Because in case of isolated atoms, how the hybridization is going to take place? It is going to undergo bond formation with another atom, na? So that atom has to be there. So when the two atoms they are coming closer, alright, when the two atoms they come closer of similar, two similar atoms or two dissimilar atoms of comparable energy, so to say, they come closer, then what happens? When they come closer means what? Energy is released, and this release of energy only allows the electron to migrate or to jump from the lower subshell to the higher subshell, from the inner subshell to the outermost subshell. For that purpose, hybridization does not take place in isolated atoms. Remember, this is one of the conditions. Alright. Now, only those orbitals which have approximately equal energies and belong to the same atom or ion undergoes hybridization. Remember the conditions. Okay. Now, next is only the orbitals present in the valence shell. Of the atom are hybridized. Only the outermost shell, the valence shell means outermost shell, they only undergoes hybridization. Because everything takes place in the outermost shell. Innermost shell does not participate. Neither in any bond formation. You have read it in valence bond theory, molecular orbital theory, in any particular theory. You have studied the innermost shell, because innermost shell is completely filled. They do not participate. Always the valence shell, they participate. That is the outermost shell. So here also in case of hybridization, That is, the orbitals present in the valence shell of the atom undergoes hybridization. We can say this is the second condition or the third condition. You can say that. Now, that is, promotion of electrons is not the essential condition for hybridization. It does not mean that whenever the hybridization is going to take place, electrons will be promoted from lower to the higher. It is not necessary. It is one of the conditions, but not the necessary conditions, I mean to say. That is the only condition. No, it is one of the conditions. Like in case of beryllium I gave you, in case of what you can say, carbon I gave you. Got it? So in those cases it is there. Got it? But it's not the only conditions. We'll come to it later on. Some other examples you'll see it. Now, it is not necessary that all the half-filled orbitals, got it, must participate in hybridization. All the half-filled orbitals. It is not necessary. Similarly, it is also not necessary that only half-filled orbital participate in hybridization. As it is not necessary that only half-filled orbital participate in hybridization, and also it is not necessary that all the half-filled orbital participate in hybridization. Got it? Clear? So it is not necessary that all the half-filled, even, remember, even completely filled orbitals, got it, with slightly different energies can also participate in hybridization. Completely filled orbitals with slightly different energies, like you know that px, py, pz, even if they are degenerate, belong to the same energy level, but due to the arrangement, got it? Now px, if you take horizontal according to the coordinate axis, if px is horizontal, py is vertical, we can say that, perpendicular, 90 degree, and pz is perpendicular to both x and y. So are they in the same, they are having the same energies? No, they have slightly different energies, px, py and pz, even if they belong to the same energy level, but still then they have got slightly different energy. So that will do, that will help in hybridization. Alright, that difference in energies will help in hybridization. Little bit amount of energy which is different. You have read it in molecular orbital theory, that px and py undergoes pi bond formation. You have read it now, pi to px and pi to py and sigma to pz. Alright, sigma y it is because sigma they undergo head-on overlapping, and pi to px and pi to py undergoes lateral overlapping, sidewise overlapping. For that reason I am saying pi, sidewise, lateral. Alright, pi bond is sidewise overlapping is taking place, lateral overlapping is taking place, and sigma to pz I am saying. Why sigma? Because head-on overlapping is taking place. So slightly they have got different energies. You have seen it also, that they are different energies because they are filled in different levels. Got it? You have studied. So even if, remember it, even if it's completely filled orbitals, but they have slightly different energies, they participate in hybridization. So these are the necessary conditions for hybridization, so to say. Now there are certain characteristics or some salient features of hybridization. When hybridization is going to take place, then what are the changes is going to take place, or what are the observations you will see, what are the characteristics you will see, that also you may note it down. That number of hybrid orbitals formed is equal to the number of atomic orbitals, always. I said you just now, I gave the example of pink paint, which is 2 box you will be getting it, or 2 bottles you will be getting it of white and red, always, remember it. So number of hybrid orbitals produced is equal to the number of atomic orbitals which is combined. Alright, that's very important. It is mixed. So 2 atomic orbitals gives rise to 2 hybrid orbitals. In case of molecular orbitals also you have seen it, the same thing. Now hybridization never takes place in isolated atoms. Already I have explained you this particular thing, why it does not take place. Then higher, the bigger lobe always undergoes hybridization, the smaller lobe does not. You can say, I told you the reason behind it. Now, the hybridized orbitals are always equivalent in energy and shape. That we know from the definition itself. The hybridized orbitals are always equivalent in energy, equivalent in shape, we can say that. For that reason only, I told you in the last TV that methane molecule is tetrahedral, where the bond length, the bond energy, the bond angle, everything is identical for all carbon-hydrogen bond. Otherwise, if you see theoretically, 3 bonds are same and the 4th one is different. But practically it is not so. Because practically when you are talking, you're talking about hybrid orbitals. When theoretically you're talking about atomic orbitals. So you know that atomic orbitals do not combine and they form, but you can say the methane molecule or any other organic molecule containing carbon atoms present in it. Alright, so how do they combine? First they redistribute their energy. Alright, then only they combine and they give rise to hybrid orbitals. So whenever I talk of practical concept, that means I am talking about hybrid orbitals. When I am talking about theoretical, that means I am talking about atomic orbitals. Alright. Clear? So, but there is no difference between theoretical and practical concept. I've said you when you read about hybridization. When you come to know about hybridization, there is no difference. Alright, where there is no difference, because I said you already that atomic orbitals, again and again I am saying, this is what is very important. You need to understand this, because I am going to draw the diagram. At that time, you need to understand that atomic orbitals are never combined to give rise to a molecule. Alright. Clear? They do not combine directly. First, they redistribute their energy in such a manner that each orbital get equal amount of energies. Then only they combine and they give rise to hybrid orbitals which have same energy, shape, size, everything is identical. Alright. Now, there is after that the hybrid orbitals form more stable bond than the atomic orbitals. Hybrid orbital formed has got more stable bond. Why stable bond? Because energy is equal. No? It is same throughout, and energy is released also. Less amount of energy is being left, alright, in the formation of that particular compound. So minimum is energy, maximum is stability, alright. And the hybrid orbitals are directed in a definite directions. For that reason I said that it gives the shape of the molecule. Hybridization also gives you the shape of the molecule. They are directed in definite direction, and they arrange itself in such a manner so that they have minimum repulsion and maximum stability. Minimum repulsion between what? Between the hybrid orbitals. They arrange itself. The hybrid orbitals arrange themselves in such a manner so that they have minimum repulsion and maximum stability. We can say that. So these are the characteristics, and one more that is we will be adding it here. Few more I'll be adding it here. That when hybridization is taking place, then we will be seeing that different kind of hybridization is taking place. Different types of hybridization is taking place. That is, you will be seeing sp3 carbon-carbon single bond, sp2 carbon-carbon double bond, sp carbon-carbon triple bond. Then you will be having sp3d, sp3d2, sp3d3. In this way, different types of hybridization will be taking place. Different types of. Alright, how do you come to know? I will say you. Alright, but here, one thing you remember is that the size of the hybrid orbitals decreases with increase in the s character. Alright, the size of the hybrid orbitals decreases with increase in the s character. Means we are having, let us say, sp3, then sp2, then sp. Alright, so let me write in this way. Clear? So sp3 means, see how to calculate percentage of s character. How do we calculate? sp3 total, how many orbitals we are having? 4. 1s and 3p. 4. So s is how many here? 1. So 1 by total is 4. Alright, 4 or not? See, 3p and 1s total is what? How many orbital? 4. We got it. So s character I am calculating it. 1 by 4 into 100% percentage. So how much you got it? Nothing but 25. So here it is 25%. Similarly here total is 3. So 1 by 3 into 100%, it will be how much? 33.33%. And here sp total is 2. So s is 1. So 1 by 3 into 100%, how much it is? 50%. Here s character is 50. Here it is 33.33%. Here it is 25%. We can say that. So what I said you, size of the hybrid orbitals decreases with increase in s character. The size of the hybrid orbital decreases. Here the hybrid orbital is going to decrease. So here you will find it out. sp is taking place in which kind of what you can say molecule? You will see carbon-carbon triple bond. Here it takes place in carbon-carbon double bond, and here it takes place in carbon-carbon single bond. Alright, sp3. So you know that, or if you do not know, you write it down that carbon-carbon triple bond, the bond length is between carbon-carbon triple bond, the bond length is how much it is? 1.2 angstrom. Here the carbon-carbon is 1.34 angstrom, and here the carbon-carbon single bond is 1.54 angstrom. We can say that 1.54 angstrom. So this is not there, okay? Don't get confused here. It is 1.54 angstrom. Clear? This is 1.54 angstrom. Here one bond is not missing. I am not putting here, I am putting it here. Understood? Otherwise you will get confused. You will write it as 11.54. It's not 11.54, 1.54 angstrom. This is the bond length between carbon-carbon. Because I said, again I repeat, that the size of the hybrid orbital decreases with increase in s character. See, size is decreasing, so bond length is also decreasing. Size will decrease means they will come closer. So when they will come closer, the bond length is going to decrease. So hence it is stronger bond it is. So sp triple bond is very strong. See the bond length 1.2, and here the bond length is 1.34. Here the bond length you see is 1.54. Alright, so this you come to know. And more is the S character. Remember it. More is the S character here. More is its electronegativity. More is its polarity. We can say that. More is the S character. Remember it. More is its electronegativity. More is the polarity. Alright, clear? So in this way, you have read it in this one in chemical bonding. I have said about it. So bond length decreases while bond energy increases with increasing S character. Just now I said it. Bond length is decreasing and bond energy is increasing. Alright, bond energy, I'll tell you when I teach you, that is triple bond, double bond, single bond, the hybridization, I'll tell you what is the bond energy and all those things. At that time, I'll tell you about it. So, hybrid orbitals, it's overlap to a greater extent in case of triple, then double, then single bond, we can say that. Alright, so due to electronic repulsion between the hybrid orbitals, they remain at the maximum distance apart due to electronic repulsion. But the arrange itself, again and again I am saying in this particular one, because you might be having this doubt that how the shape is coming. They itself arrange it. In VSEPR theory also studied. They itself arrange it. Here also they itself arrange it in such a manner that the force of repulsion is minimum and the stability is maximum. Got it? So hence they remain maximum distance apart. Clear? For that particular purpose we can say that. So now next is the orbitals of one and the same atom participate in hybridization. Alright, that is we come to know about it. So this is about the characteristics of hybridization, so to say. Thank you.